Hello and welcome to Shape Math. In this video, we're going to discuss the principles behind Shape Math. But first, whom should use Shape Math? Shape Math is designed for dyslexics and dyscalculics. This is because these two groups of people like to see how things are put together mechanically, but have trouble with math taught the conventional way. Next, we'll discuss the principles underlying the Shape Math program. Shape Math works on a few basic principles that allow it to maintain ease of use and flexibility. The first principle is there is a 10 base shape. Depending on how other shapes fit into this 10 base shape, you're able to do addition, subtraction, multiplication, and division. All the numbers 10 or lower fit into the shape of 10. The next principle deals with the one triangles. All the shapes in Shape Math can be made out of one triangles. You can see this in the shape of 10 made out of all one triangles. Another principle of the one triangles is all the one triangles are interchangeable. This is possible thanks to our next set of principles, the ones dealing with the zero spacers. You may have been wondering what these black lines were when we showed you the shape of 10 made out of all one triangles. These are called zero spacers, and they serve a few essential purposes in the system. First, they assist in dyslexic visual tracking, separating the inside shapes from the outside shapes. As you probably already know, visual tracking causes dyslexics and dyscalculics a great bit of difficulty. I should know, I am both of these. The second purpose of the zero spacers is they allow all the one triangles to be the same size, regardless of where they are in the 10 base shape. This is important because, as mentioned before, all the one triangles are interchangeable. These zero spacers make up the gap between these two areas. Otherwise, some of these one triangles would have to be large and misshapen to make up the difference, or the outside shape of 10 would have to be irregular. This irregular shape of 10 would be much harder to use for mental visualization. The final purpose of the zero spacers is as a representation of zero. You probably guessed that from the name. If you take these zero spacers out of here and arrange them like this, they make one corner of the 10 shape with nothing in it. This is how zero is represented in Shape Math. This will come in handy when we get to the written form of the Shape Math numbers a little bit later. But for now, we'll move on to the principles behind color. Color serves as a conceptual reinforcement for Shape Math. The numbers 5 and lower go in a gradient. The cooler the number is, the lower it is. The higher the number is, the warmer it is in color. It goes blue for 1, green for 2, yellow for 3, orange for 4, and red for 5. The numbers above 5 are made up of the numbers and the colors below 5. This means the reason that 8 is orange is because it's made up of two 4s. This is one of the ways that the simpler aspects of Shape Math reinforces the more complex ones. The idea of the colors reinforces the idea of division. However, some numbers do not have two of the same number that can make them up. This is why 7 and 9 are made up of two different colors. They're made up of a 5 and an additional amount. 7 is made up of a 5 and a 2, and 9 is made up of a 5 and a 4. You could, of course, make 7 and 9 out of two different numbers than these and get the same outside shape, which brings us to our next set of principles, the Shape Math outlines. It is the outline of a shape that determines what the answer to a problem is. You can make the same shape many different ways. You can make a 7 out of a 3 and a 4, or you can make a 7 out of a 5 and a 2. This section of the web application is called the Outlines tab. It shows all the shape math outlines for numbers 0 through 10, so you can practice different ways of making them. You may have noticed that there are two different forms of two numbers, 3 and 4, which brings us to our next principles, the inner and outer shapes. There are two different forms of 3 and 4. This form of 4 is called the inner 4, and this form of 4 is called the outer 4. The reason the inner 4 is called the inner 4 is because inside of the shape of 10 made out of all 1 triangles and the 0 spacers, the inner 4 is completely surrounded by the 1 triangles and the 0 spacers. On the other hand, the outer 4 touches the outside of the 10 shape, which is why we call it the outer 4. Both forms of 4 are made out of the same number of 1 triangles, 1, 2, 3, 4, and 1, 2, 3, 4. The only reason the outer 4 looks a little bit bigger is because of those 0 spacers. The same principles apply when it comes to the inner and outer forms of 3. They are both made out of the same number of 1 triangles, and the inner 3 is completely surrounded by the 1s and the 0 spacers when it's inside the shape of 10 made out of 1s and 0 spacers, while the outer 3 touches the outside of the 10 shape. The next set of principles deal with the written numbers. One of the goals in shape math is to make the student capable of working independently without needing to rely on the digital shapes. One of the ways we do this is with the written form of shape math. These are the written shape math numbers 0 through 10. They look very similar to the regular shape math numbers with a few small differences. The first obvious difference is they don't have color. This way, you don't need any special writing implements. Wherever you can write the regular Arabic numerals that we all know and love, you can write the shape math numerals. Because the written numbers don't have color, we needed to change or slightly alter a few numbers. 1, 2, 4, 8, and 9 needed to be altered slightly when writing. The numbers 1 and 2 have the shape of 0 around them to distinguish them from 5 and 10. Without color, 1 and 2 could be confused with 5 and 10. Having the shape of 0 around these numbers also shows the relative size in the context of the 10 shape. This is because 0 is one corner of the 10 shape with nothing in it. The numbers 4, 8, and 9 were altered to help with dysgraphia and others with handwriting difficulties. These extra long lines here emphasize the difference between a 4 and a 5, an 8 and a 10, and a 9 and a 10. This way, even if these numbers are written poorly, they can easily be distinguished from each other. This is similar to how some people put a slash through a 7, so it doesn't get confused with a 1. If you would like to see the written form of shape math in action, you can click on this part of your screen to see a written shape math problem in place value, no less. Otherwise, we will move on to the next set of principles, the shape math patterns. Alright, we'll move on to the shape math patterns. Shape math is well capable of doing problems 10 and higher. In this section, we're going to talk about how to use patterns in something we like to call direct representation. Similar to how you can group together shapes below 10, you can group together patterns above 10 with the same ease. This is the pattern of 50. When making patterns below 50, you're trying to build up to the pattern of 50. For example, this is the pattern of 30, this is the pattern of 40, and this is the pattern of 20. They're all constructed like the pattern of 50 with parts removed. The pattern of 100 is made up of two 50s, like this. You can also make different combinations of patterns to get the number you need. For example, this would be the pattern of 70. It's made up of a 50 and a 20. This is very similar to how we made a 7 out of a 5 and a 2. In combinations with numbers below 10 and the patterns above 10, you can make many different numbers, such as 77. You can pretty much make any number you need. Now back to the pattern of 100. The reason these tens are arranged like this is each corner of the tens are touching, so your mind groups them together as a single object. But there is space in between the tens, so you can also easily distinguish the different parts or the different tens from each other. These techniques are used to help overcome working memory difficulties. These patterns are easier to remember and give structure when imagining larger numbers. This allows these techniques to not only be used with the digital shapes, but for mental calculation as well. There are also techniques for visualizing numbers above 100, but you'll have to go to shapemath.com and purchase a ShapeMath subscription to find out about those. I can't give away all the secrets here. Now we'll move on to the principles underlying our next concept, time conversion. The next principle deals with what we like to call time conversion. This is how ShapeMath converts between minutes and seconds, seconds to minutes, hours to minutes, and minutes to hours. This is the pattern of 60. It's made up of 6 tens. It's like the pattern of 50 with one more 10 on top. To help the students remember this pattern, we tell them that it's like a little person. You have the 10 on top, which is the head. You have the arms, the torso, and then the legs. With the 3 patterns we've gone over so far, the 50, the 60, and 100, we can start converting between different units of time. Let's say you have 2 hours, and you want to know how many minutes this is. First, we arrange 2 60s. Each of the 60s represents an hour. We can recognize that in between the 2 60s is the pattern of 100. We can take off the amount above 100 and put it over here. So now we have the pattern of 120, or 120 minutes. This process also works in reverse. If you had 120 minutes, and you try to see how many 60s you have, or how many hours you have, we would take these 10s and put them onto the 50s, making them 60s, giving us the pattern of 2 hours. I hope you have enjoyed this demonstration of the principles that make ShapeMath work. Don't forget to subscribe to our YouTube channel, and make sure to check out shapemath.com to find out more about ShapeMath, the number system that fits. Or you could call 412-527-6988 to speak with a ShapeMath representative. And of course, thanks for watching.